Shanghai, city of the future. Vying for attention in this fast-growing, high-tech metropolis is some of the world's most cutting-edge architecture and ever more extraordinary feats of engineering.
There is a great competition for creating these landmark buildings. The clients have always asked me, build me a landmark.
Architect Martin Jochman has been set a seemingly impossible challenge: to design a radical new hotel that will stand out in this hotbed of innovation. But the unique site totally defies convention. It must be built 90 meters below ground level in an abandoned, flooded quarry.
When I came here almost 12 years ago, it was just a hole in the ground. Now, over the years, against all the odds, this has changed.
Martin's master plan is one of the world's most inventive buildings. Resembling something from a James Bond movie is the InterContinental Shanghai Wonderland. This giant quarry hotel spans 100,000 square meters and is the first of its kind on the planet.
这里面是吧？中间的这个池子是吧？
Helping to realize this epic multi-million-dollar fantasy project is chief engineer Xiaoxiang Chen.
I'm very proud of being a part of the project. Everybody is excited because it is the only one in the world.
What, at ground level, first appears to be a two-story building is in fact only the tip of the 337-room hotel. It projects out from the precipice and descends to the base of the quarry 90 meters below. The glass wall in the center is designed to look like a waterfall cascading to the quarry floor. This will be flooded to create a lake, submerging the two lowest floors. It's an epic engineering challenge once thought impossible.
Such unusual location brings its problems to be solved. These can be summarized into the building shape, the seismic implications, and the fact that the building is partly underwater.
Not only must it be waterproof and earthquake-proof, but the engineers are also faced with a giant problem that looms all around them.
The biggest problem when we started designing this building was associated with the quarry itself, the composition of the rock. This rock has come out as part of volcanic eruption, and it has cooled rather quickly, which means some of it is quite solid, but some of it is crystallized and very, very crumbly. I can demonstrate how this crumbles easily in your hands. This problem had to be really solved before we could start on the main part of the construction, both for the safety of the guests, but also for the safety of the workers on site.
Failure to secure the unstable cliffs will mean disaster for the project. Building this groundbreaking hotel will need some impossible engineering from the past. The problem with rock walls is that they're prone to collapse. One reason why more discerning humans ventured out of caves and into homes made of other materials. The Nabateans took rock construction to the next level, carving Petra's fabulous sandstone temples and tombs. But over the centuries, many have crumbled. The presidents of Mount Rushmore are hewn from the toughest granite. But even they need a facelift from time to time. Any hairline cracks are filled as soon as they appear.
Hey, looking good, Abe.
But there's one device that's so effective at holding up rock walls, that climbers like engineer Dan Dickrell are willing to trust it with their lives.
Oh, here it gets spicy. Woo! So right now I've climbed this rock face. I'm hanging in the air, and all of my weight is going through that rock bolt, which is anchoring me to the surface. So the rock bolt is a smart and simple idea developed over 100 years ago.
And this simple idea might hold the secret to solving the problems at the Shanghai Hotel. In 19th century America, lead mining was big business. The #1 producer was the St. Joseph Lead Company, and their mine in Bonne Terre, Missouri was their biggest and most profitable.
This incredible piece of engineering ambition was, at the time, the world's largest man-made cave at over 375 feet high, and it was also the first deep earth lead mine in the world. It's really quite impressive.
This vast cathedral of a mine was operational for 97 years.
This place is epic.
When it closed in 1962, the water pumps that kept the tunnels dry were turned off, creating a 17-mile-long underground lake. And now, the only way to get around is by boat.
Mining this lead is no easy task. The miners are looking for the ore in thin veins which are spread through the rock. They have to chip it out in large chunks of ore. Now, if we look over here, some of the richest veins extend vertically, 375 feet from the bottom to the top.
So the question was, how to reach that precious metal buried in the walls, over 100 meters off the ground. St. Joe's was a forward-thinking company that prided itself on innovation. It recruited so-called experimental engineers, whose job it was to devise ways of extracting every ounce of ore. These early problem solvers faced the challenge of scaling the heights of these walls.
So this is what they came up with. The trapezes, a series of scaffolding suspended from the ceiling. The workers would work chipping away almost a skyscraper above the ground. The tools they used weighed 50, 60, 80 pounds. The men themselves were large, the rocks were heavy. Such a large amount of weight suspended above that cavernous drop.
And responsible for bearing all that weight, the newly invented rock bolts.
This is actually an original 100-year-old split rock bolt. You can see the split on the end. How would this be installed? Drill a hole in the ceiling and then pound a piece of oak in, which effectively would be a wedge that when you put the bolt into that hole and pound it in, the wedge would slowly split open the bolt, creating a very, very strong anchoring point.
Trapeze mining was a great advance, but it was these rock bolts that proved to be the real innovation.
It was noticed that after the scaffolding was removed, the rock bolts that still remained in the ceiling were holding up the loose rock that otherwise would cave in.
Securing a rock face is precisely what the team in China need to do. So how do the rock bolts achieve this?
I have a container that I'm going to fill with loose gravel. Now the thing about this container is it doesn't actually have a bottom. So now what we need to do is insert the bolts down into the temporary bottom. All right, let's put some gravel in here. I'm going to take the top washers and nuts and tighten them down. This will create a compressive force that binds all of the gravel together.
This will replicate the forces at work when bolts are inserted into a crumbling rock ceiling.
I'm optimistic. I'm optimistic this is going to work. I'm going to need a bit of help, so I'm going to have Adam from the Bonne Terre mine come in and assist me with this. There we go. All right, Adam, slowly try and take the bottom off, temporary bottom. What do you know? It worked. You wouldn't think it's possible, but check it out. It's really, really solid. Management concluded that long bolts placed close together would safely knit the loose rock in the ceiling above us. Without knowing it, the miners here at Bonne Terre had inadvertently invented real innovation, which is used all over the world today. What an accomplishment.
So, how can the engineers in Shanghai take this century-old discovery and put it to work?
Here are the rock bolts, which are a very important part of the stabilization of the cliffs. The rock bolts are in positions where they can be most effective in securing the cliff face on a certain grid.
First, the rock walls are blasted in several places to level them off. Then they insert 6,000 supersized rock bolts. The mega bolts, measuring up to 15 meters in length, are placed at regular intervals to make up a giant grid across 5,700 square meters of rock face. For added security, the whole area is covered with a layer of metal mesh, then sprayed with a thin layer of cement called shotcrete.
The mesh, together with the shotcrete, will prevent the crumbly face of the cliff falling down and endangering the guests and the visitors. This process is quite unique to this project. It has never been done on this scale before. It is in fact one of the great challenges that had to be overcome to be able to end up with this amazing building.
And Martin has the tech to make the most of seeing his design come to life from every angle.
Every time I come here, I'm amazed about the transformation of the site. To be able to actually get a picture from the same angle as you're rendering and then be satisfied that this is really as close as you can get to your concept vision, that is very satisfying, actually.
But this unique design has to be built to withstand the most destructive forces on the planet.
There's no precedent for this type of building in terms of seismic design.
Embedded deep underground, how could they make this impossible piece of engineering earthquake-proof?
Sometimes in the midnight, I wake up to think of the problem I should resolve.
In Shanghai, China, engineers are facing a subterranean challenge. This giant hole in the ground is the location for their city's newest state-of-the-art structure. A mega hotel built 90 meters below ground level.
Progress is going well. We almost finished it. But this project gave us many big engineering challenges.
Taller than the Statue of Liberty, the hotel is essentially an inverted L shape. The 10,000-ton steel mainframe is set into the base of the quarry, with the wider top section stretching out onto the clifftop above. But it has to be strong enough to withstand anything Mother Nature can throw at it, and this is earthquake territory. There is no greater destructive force on the planet than that generated by an earthquake. And China is one of the most active seismic regions of the world. The point of convergence of the Indian and Eurasian tectonic plates, the country is riven with fault lines. Engineers here are experienced in using methods to combat earthquakes in conventional buildings. But nothing like this has ever been attempted before.
There's no precedent for this type of building in terms of seismic design. So this creates a completely new problem to be solved, had to be done from the first principles with the latest engineering technology.
To help it withstand the forces of an earthquake, massive foundations are required.
As you can see, the foundations are immense, almost 50,000 cubic meters of concrete. It had to be so to give the steel structure the rigidity it needs, to embed the steel beams and columns into it quite deep, to satisfy the seismic regulations. But this throws a new problem: how to place such large quantity of concrete so deep.
In order to get such a vast amount of concrete to the quarry floor, the team need to come up with an innovation that defies gravity. The concrete for the foundations has to be mixed at the surface, then delivered to the base below. But sending it straight down a vertical drop means it's traveling too fast. The mix would start to separate, and by the time it reaches the bottom, it's unusable.
Normally on a building site, concrete is pumped upwards. This was placing it 90 meters down under gravity situation, so completely new method of pumping had to be devised for this.
It's up to Chief Engineer Xiaoxiang Chen and his team to come up with the solution.
During the construction, we have encountered numerous challenges, and sometimes in the midnight, I wake up to think the project, to think the problem I should resolve.
The team need to find a way to slow down the concrete's rapid descent to make sure they end up with a stable mix. So they insert additional mixing stations. The concrete drops down the first 15 meters, then enters the station. It gets remixed and sent on its way, passing through 2 further mixing stations. So once it reaches the base, it's the perfect consistency.
With lots of hard work, I'm very happy about the result.
But incredibly, 50,000 cubic meters of concrete on its own is not enough to protect it from an earthquake. Due to the hotel's unique design, the team need an extra engineering solution to prevent it from being pulled apart by opposing forces.
It is a tall building attached at both ends, and in the event of earthquake, both parts of the building move in different direction and different speed. So this creates completely new problems.
To prevent disaster, the engineers have to find a way to protect this unique structure. When the Earth moves, the only survivors are those that can somehow go with the flow. The Incas built Machu Picchu from precision-cut stones with no mortar. The stones are said to dance through the tremors, then fall back into place. China's Forbidden City has withstood over 200 earthquakes, thanks to an interlocking joint which spreads the impact of any tremors. What these techniques have in common is the flex factor. Italy has suffered centuries of devastating earthquakes, more than any other European country. So engineers here have been developing new ways of building which won't yield to the forces that regularly rock the landscape. These might hold the key for the team in China.
During the last 40 years, we learned to build the structures safe to withstand earthquakes.
Seismic protection engineer Samuele Infanti works for the company that designed Europe's first bridge engineered to be earthquake resistant. The Somplaggio Viaduct. Its twin decks run in parallel across Lake Cavazzo. And despite being 1.2 kilometers long, it remained standing when a powerful earthquake destroyed the nearby village.
So now we are entering the village of Somplago. As we can see, more or less all the houses were rebuilt after the earthquake. But it was only the bridge surviving that earthquake with no damages.
So how exactly did the bridge remain intact? Like the Wonderland Hotel, it's attached to high ground at the top and low ground at its base. The secret of its success can be found where the underside of the road deck meets the top of its vertical piers.
The idea it was to isolate the deck above the bearings from the ground. During an earthquake, this bridge will move back and forth along the longitudinal direction.
Using a principle known as seismic isolation, the key mechanisms are the mighty bearings which cap each individual pier. These are made up of sliding metal plates which allow the deck to move freely, protecting it from tremors at its base.
We want to simulate the effect of a seismic event, and this represents a conventional way of fixing the deck to the piers.
But on the second bridge, bubble wrap is added to simulate the bearings.
We can see that now the deck is kind of isolated. You see that we can move it back and forth in all directions. These elements provide a filter-like effect. So they are filtering the acceleration transmitted by the ground moving at the occurrence of the earthquake.
Dragging the bridges will replicate the vibrations of an earthquake.
You see that this model provided the typical collapse, whilst the other survived without damages. The bubble wrap in this case are simulating the behavior of the isolators. It means that the ground will move in a very quick manner, while the deck will move slowly, and immediately after the earthquake, the bridge can be ready to survive another event, an aftershock. And this way we can avoid the damage.
The principle of base isolation has been applied to structures around the world, saving countless lives. But can the engineers in China apply the same method to this unique construction project to avoid destruction?
The structural solution is totally unprecedented and comes with the fact that it's a building fixed at two ends. In order to satisfy the seismic requirements of the earthquake, it is important that this structure can move to a certain extent.
Here in the inner atrium, the rear of the hotel looks out onto the rugged exposed wall of the original quarry and the steel framework that supports the building. It's this that provides the ultimate defense against earthquakes.
The structure consists of horizontal trusses that sit on a concrete beam. These are then connected to the vertical trusses that are firmly embedded in the mass concrete at the base of the hotel. Together they form very rigid structure, but in case of earthquake, this can still move.
The horizontal trusses are not fixed to the platform at the top. Should the worst happen, the horizontal trusses can slide back and forth and ride out any seismic activity.
It's actually sitting loosely on a platform that will allow it to move freely. This will make it possible for the building to stand out during very strong earthquake. It is a unique solution to a unique construction problem.
With the structure now earthquake resistant, the engineers must face the next impossible engineering challenge: creating rooms underwater.
There is no light in this corridor because right now we are working on the underwater space.
But how can the submerged levels of this futuristic development withstand huge amounts of water pressure?
As an engineer, we need to find a solution for that.
Here in Shanghai, developers are pouring hundreds of millions of dollars into this giant hole in the ground to create a mega hotel. The first one ever to be built in a quarry. Its architect is Martin Jochman.
Such unusual location brings many challenges. One of those is the fact that part of the building is underwater. In fact, where we are standing will be submerged.
The quarry originally had a lake at its base, which was pumped out into the canal that runs above it. But the plan is to flood the quarry again before it opens. Walkways will cross the man-made lake to a central island, and a brand new waterfall will be built on the west face of the quarry. The bottom 2 stories will be submerged below water level, and an underwater restaurant and bedrooms will be surrounded by giant fish tanks.
One of the biggest problems to overcome when designing this building was the underwater rooms and public areas.
Architecture design manager Hao Tseng is overseeing this part of the project.
You can see there is no light in this corridor because right now we are working on the underwater space. Here is our very special and exclusive room. There is no traditional window. Instead of that, we have a big aquarium here.
To make this experimental concept a reality, the designers are setting themselves a seemingly impossible mission.
Our biggest challenge is how to deal with the water pressure and how to deal with waterproof. It's very important to keep the water away from the room.
The volume of water required exerts so much pressure that ordinary glass would break and flood the rooms. In order to realize their dream of underwater living, the engineers needed to look to the skies of the 1940s. At this airfield just outside Los Angeles, engineer Dan Dickrell is finding out what the team in China can learn from one of the most important planes in wartime history, the Boeing B-17.
As a child, I built models of this. One of the most iconic bombers of the Second World War. It's absolutely breathtaking.
Known as the Flying Fortress, this heavily armored warbird was designed to penetrate deep into enemy territory to carry out precision daytime bombing.
1, 2, 3, 4, 5, 7, 8, 9, 10, starting number 3 again.
This is one of the few airworthy models left in the world.
This is the most amazing experience right now. I've done a lot of crazy things, but I think this is the best. Truly, truly amazing to be here. This is the aircraft that captured the world's imagination. It has a cruising altitude of 35,000 feet at a speed of 287 miles per hour. It weighs 29 tons. It's really, really a solid aircraft. At one point during the war, one of these B-17s returned, missing 2 out of the 4 engines, and had 180 flak holes in it like a piece of Swiss cheese. But it returned safely, which is a testament to how strong this particular airplane is. However, there was one part of this aircraft that was notoriously fragile and impractical, and that was the problem that needed to be solved.
The early versions of the B-17 had a weak spot.
The original nose of the B-17 was composed of a metal frame and large amounts of real glass. If you've ever broken a real glass, you realize glass shatters. This is obviously not great for the people behind the glass. Huge amounts of dangerous, sharp particles coming right at them.
To solve this fatal flaw, in later models this was replaced by a clear dome made of a brand new material, plexiglass. It was the invention of chemist Otto Röhm. Röhm's life's work had been the development of new plastics, but he discovered plexiglass by accident.
Röhm had MMA, which is a rudimentary acrylic in a petri dish. Sunlight hit the dish, heating up the MMA and polymerizing it, creating PMMA, which we call plexiglass.
He discovered that if it was heated, it could be molded.
So I'm going to keep mechanical strain on it while it hardens. As it cools, it will retain the shape. Yeah, it worked. It's a great material.
But crucial for aviation engineers was how it responded to stress.
Plexiglass doesn't shatter. And that particular property is what enables this aircraft to be such an effective daylight bomber.
This was a major development. The nose is one of the most tactically important spots on the plane, as it's where the bomb aimer sits. And plexiglass was not only safer, but greatly improved his visibility.
From this vantage point, you can see the view that the bomber would have. This bubble canopy. An amazing view of the target, the countryside, where the bomber was headed. This solution, it's elegant and it's beautiful, breathtaking.
This tough, transparent material could help the team in China achieve their vision. Within the giant concrete foundations sit massive water tanks.
We want the view of water tank as big as possible, but it has to be very clear. And due to the water pressure, the material has to be very thick. So we found acrylic glass. It's like 13 to 16 centimeters, and you can see it's very clean, and the people can easily see through it.
But with added thickness comes added weight. This window alone weighs more than 2 tons.
You can see the acrylic glass is very, very heavy. We need 4 people at the same time lift the chains.
The largest windows on site weigh 4 tons, used in the hotel's underwater restaurant.
So now we are standing in the biggest space underwater. This is the dining room of our specialty restaurant. You can see there are 5 pieces of acrylic glass. The big acrylic glass is more than 5 meters wide and 3.5 meters height. It's very, very big and heavy. But behind them, it's a big water tank. It's like 30 meters wide. We really want the client to feel like they're staying in the ocean.
From the watery depths of this extraordinary construction to its heady heights, the engineers still face a high-level challenge at the summit of the cliff face.
To build something at the top of the cliff is a really big challenge for us.
In their quest to create more impossible engineering. Shanghai is famed for innovative structures punctuating the horizon. A new landmark is underway, but it won't be changing the skyline. Instead, it's pushing engineering boundaries deep underground. Racing to transform an abandoned quarry into a high-spec, high-end hotel resort
那个是核心任务啊。
is a 5,000-strong construction team led by Chief Engineer Xiao Chen.
就上面这一层啊，上面但是因为下面它都是泡沫。It is the only hotel in the world built in the pit. We face many new challenges.
Building in a quarry is a mammoth operation. But the setting has provided inspiration for its biggest and most complex design feature. Dreamed up by Martin Jochman.
The glass waterfall is symbolic of the connection of the rock face, the cliffs, with the water, and the shape is itself suggesting the falling water shape, and this is the most difficult part of the whole structure. It's curved, it's irregular, it's covered with glass, so it's a great challenge to actually put it together.
A complex steel framework is being covered with over 5,000 square meters of flat and curved frameless glass panels to create the illusion of a glass waterfall.
Now we are actually inside the glass waterfall. It is a vertical circulation containing observation lifts which will take guests and visitors from this floor down to the base and to their guest rooms. When I see what's been produced, I'm very happy that my original idea that I have sketched a long time ago is there. All credit to the team, the people involved in the design, the structural design and the construction.
The next phase is to start filling the quarry pit to create the man-made lake. It will need 200 million litres of water. With such a huge volume, it's a slow process.
Filling water of the pit. I'm very excited for it. It will take 4 months to fill it, but I'm very patient.
For architecture design manager Hao Tsen and her team, there's one more challenge. An audacious final addition to make the most of this unique location from every angle.
That's a really magic and amazing view here. It is great to stand at the bottom and look up. We want to build something at the top of the cliff so people can stand at the top and look down.
The team want to somehow create a walkway right at the top of the 90-meter high cliff face. It's an ambitious plan.
To build something at the top of the cliff is a really big challenge for us. We want to build something sticking out of the cliff wall, and it should be strong and safe enough. It's really tough for us.
The solution could lie in an engineering innovation embraced by a famous trailblazer of the past. In the wilds of Pennsylvania, tumbling rivers cut through the forests of the Appalachian Mountains. It's here that a landowner threw down the gauntlet to an up-and-coming architect to design him a home. Civil engineer Scott Hamilton is here to see how it might help the team in China.
Falling Water, a truly amazing architectural building. It challenges the very landscape it sits upon, and many have described it as America's most famous house.
The Falling Water House is the brainchild of innovative architect Frank Lloyd Wright.
Falling Water was commissioned by wealthy Pittsburgh businessman Edgar J. Kaufman. Kaufman wanted a home where he could hide away in nature, yet it had to be a big enough space where he could entertain lots of people.
Like the hotel in China, the location of the site proved the biggest challenge. Surrounded by rock faces and a river, the plot of land wasn't big enough for the house Kaufman craved, so he left it to Wright to find a solution.
What Wright came up with is this: a series of rooms and gigantic balconies with seemingly no support beneath, essentially creating spaces in thin air.
Wright pulled off this balancing trick by anchoring these platforms so deeply into the central chimney they didn't need any other support, providing he made them strong enough.
This will be my falling water house, just like Wright's design. So we take our ground level balcony. As you see, if we put it out, we need something to counterbalance. Wright used his chimney stack and the main structure to do that. So I'll use a brick. And then we have our next level. And again, we need something to counterbalance that. And then we have our top level. And we'll counterbalance that. So here's my falling water house model. So let's have a look with what can happen when things go wrong. As we take our load and we put it on our balcony, we see it starting to bend down. As we increase the load, we see it bending more and more. We get closer to our limits and we have a failure.
So Wright's ingenious solution was to reinforce these cantilevered floors with lengths of steel.
So there we have our reinforced cantilever. So let's give it a go and see what happens. We put our load on and we see it holds, just like we want it to. This design relied on a careful balance of both geometry and tension and compressive forces. If one part of this was off, the whole structure would fail. It was so radical for its day. Falling water is a national treasure and a truly great engineering feat.
Innovative design relies on impossible engineering. Wright's cantilevered platforms started from 10 meters above the water below. In China, they're 8 times that height. This is the Skywalk.
You are 80 meters high above the bottom of the quarry.
To create this impossible structure, the team turned to Wright's cantilevers.
We use cantilever series to support this skywalk. We cut holes into the rocks and insert many reinforced bars to build such a horizontal concrete base.
Using the cliff itself as the anchor point, 42 holes were drilled up to 2 meters deep. Steel beams were then inserted to carry the 74-meter-long stretch of reinforced glass.
It's a wonderful engineering feat. We are using ideas that are 100 years old, mixed with modern technology. I love it up here. That gives you the best possible view of the amazing engineering that went into building this hotel.
"12 years in the making, from the first concept to 5-star reality. The InterContinental Shanghai Wonderland is almost ready to open its doors to the world. Creating this unique subterranean structure has been an epic undertaking.
When I first saw the site, what I saw is really, really incredible. Working on this project is like a dream come true.
The engineering challenges in turning this abandoned quarry into a luxury resort have tested those involved to the limit.
The whole idea seemed too fantastic to be realizable. I'm happy to say that the results are quite amazing.
By drawing on the great pioneers who've gone before.
It's absolutely breathtaking.
Adapting, supersizing, and creating innovations of their own. The engineering and architectural teams of this veritable wonderland have succeeded in making the impossible possible.
This is the most important project in my life. When the first guest arrive, I will want to cry. I love every part of the hotel.